Bismillah ar-Rahman ar-Rahim. Welcome back to our course, Deep Learning for Computer Vision. Today we'll continue our work on the neural networks and the machine learning approaches and concepts. Our today's concept will be about the backpropagation and the cost functions. So what is the backpropagation? What is the purpose of using this backpropagation? Why it is embedded in the neural networks and in machine learning? Also, how we can minimize errors and how we can define the proper cost function in order to obtain desired outputs. So, in the session guidelines, you can see here many topics or items: backpropagation concept, advantages of using this backpropagation, in simple understanding and with some details regarding the mathematical description of the backpropagation. In fact, the backpropagation is accompanied with some, let's say, complex mathematical descriptions, especially when we talk about partial derivatives. We'll try to simplify this as much as possible. Also, what are the cost functions that we can use it, and what we can do? What is the main purpose of having proper cost functions when we apply the backpropagation? Let's go and see what is the main idea behind the backpropagation. So in general, suppose that you are doing a neural network and you are feeding your inputs to the system, and the output you can get your desired outputs, or the output that can be very close to the desired outputs. Now, suppose that your output is not as you required. So what to do in this case? You need to modify and update the values of the weights in the and the biases in the layers, in the layer and the output layers, and you may change also the type or the parameters in the activation functions. So in this case, what will happen if you modify these values? On what basis you can do this? So sometimes it's very easy to understand or to comprehend this way. When you get an output, you can propagate back this output and find the error between the desired output and the actual or the real output, and see the error and try to modify and change these weights according to the rate of change in the output. So this will lead us to have the backpropagation. So backpropagation is a process involved in the training, usually in the training stage of a neural network. It also involves taking the error rate. So when you apply the input and get the output, this is the forward propagation. And in this case, when you get the output and you want to update the weights and the parameters, hyperparameters in the system, usually you need to propagate back into the input by measuring or finding the error of the rate of change, or what is the error rate when you apply the forward propagation. This will lead to the following action. When you have a high error rate, you modify the values and see what will be the output. Then when you get a new output, you will see what is the change that occurred in this case. And when the change is going lower, or the error will be lower, in this case, you need to either to increase or decrease the weights and get the outputs this way. And you repeat the process until you get that you do not need to apply more feedback or backpropagation, and you are not very concerned with fine-tuning more and more the weights and the biases and the activation function parameters. So in neural networks, the proper training is very important in any system, whether it is deep learning or shallow neural networks or deep neural networks or convolutional neural networks, regardless of the type of the network. In this case, the training stage is very important because you learn the parameters in the system or in the network by applying the training, to the input data set to get the desired outputs. So now when you do this training, it is always associated with the topic or the implementation of the backpropagation in almost, maybe not all, but almost all the neural network systems, and deep learning maybe also the same thing. Now, The topic or the idea of the propagation is not very clear for many of us. However, we'll try today to uncover this topic as much as possible with using simple explanations. So, what are the advantages of backpropagation? So, why we need the backpropagation? As I have just mentioned, that when you have an error between the output desired and the actual output, this error can be backpropagated this to reduce this error. This can be done using the cost function and the backpropagation. So by modifying the values of the weights, the biases, maybe the activation function parameters, you will be able to reduce the error. As you repeat this process many times, you have iterations, you will get your desired output. Your actual output or the real output will be very close to the desired output. And this is why we use the backpropagation. I'm repeating this because it's very important to comprehend the main idea of the backpropagation. Now, what are the advantages of the backpropagation? Here we have many issues here. The main thing is that there's no need for previous knowledge about the neural network. So what does that mean? When you have weights, biases, and other parameters, in this case, if you want to train the system, train the neural network, you need just to choose very, let's say, random values for the W values, for the B values, and for other values as well. In case when you use backpropagation, why? Because you rely on the backpropagation to correct and to fine-tune these values or these parameters. So in case of having the backpropagation, there's no need or there's no need for a previous knowledge. So you are not asked to, let's say, or you are not forced to look for specific values for the input values for the W and the B values for other parameters also. In this case, you just pick these values randomly and continue your work, and the backpropagation will take the initiative and will take the main let's say problem solution task in this case. The other point is it's straightforward to program since there are no other parameters besides the input. So the backpropagation doesn't require additional parameters. You just need to find the rate of change or the error rate and propagate back and try to correct the values of the parameters like WB and the activation function parameters. Moreover, it doesn't also need to learn features of a function, speeding up the process. So in the backpropagation, there is no learning issue and of features or of specific features of the inputs. So in this case, you just need to apply, as I said, the rate of change in the error. And this means that your system will be also working very quickly and with a good speed. The backpropagation is flexible because it's simple and applicable to many scenarios. So when you apply your system, let's say for a given data set, and you now want to test for another data set, or you may apply the same system or the same neural network in another application that is very close in its nature to your designed problem. In this case, the backpropagation will take the advantage and will take this responsibility to modify and fine-tune your parameters according to the new inputs, regardless of whether they are the same or very close, or they are a little bit different from the original dataset values. And this is one of the good things that can be obtained using the backpropagation. So it's a good question. Wow, it's okay if you have backpropagation. So is there any limitation for using the backpropagation? I'll leave the answer to this question for you and hope that you will span and search the net to find a proper answer for this question. Of course, there are limitations. Now, in order to comprehend the backpropagation simply, let's see this flow chart, or let's say this block diagram. Here we have the network. This is our network. Okay. Now, what we're going to do, we apply the input at this place. Okay. In the input here doesn't mean the input from the early stages, maybe at the later stages. Now we calculate the error between the output. So we have here, we get, let's say, y value and y dash value, and we calculate the error at this location or at this in this block. Now we find whether the error is minimum. Okay, if the error in this case is very low, or it is acceptable for you to stop your working, or you need to continue. If it's not a minimum, no, you go and update the values of the parameters like W, like A, like B values, and feed it back to the system and wait for the new input after the modification. You repeat the same process again and again until you get the error minimized as you needed, as you required from the beginning. And when the answer is yes, you need here to stop, and your model is already trained, and it's ready to be applied to the data set in case of the training. I mean the training data set. Okay. So first step, calculate the error. How far is your model output from the actual output? So the error, this needs that you have to pick as a specific or particular cost function. What is the error that you want to calculate? Next, if this error is minimum, check whether the error is minimum. If it's okay, you can stop. Otherwise, you need to go back and find the modification that you need to do on your parameters. So you need to update. If the error is big, you need to update the weights and biases, and maybe and recheck the error again and again until you reach a minimum that is the desired value of this error or this minimum value. Now, if the error is minimum, the model is ready for production, and you can feed now your inputs from the testing data set. We'll start for dummies. Let's say we have an input. As you see here, we have a very simple relationship between the input and the output. It looks like that. We multiply the input by 2, 0 by 2, 0, 1 by 2, 2, 2 by 2 equals 4. So let's say that we have selected the value 2 instead of 2, the weight, in this case, the weight. Here, we selected this weight as 3, and we have the value of B for all steps as being set to 0, just for simplicity. So now we just multiply, we find the output value of the system output, having the weight W equals 3. So we multiply by the value by 3, so we get 0, 0, 3, and 6. This is the first step. Next, what we can do, this is the flow chart or the table for our calculations. So all these values here. Okay. So having the inputs, having the desired output, here the model output after multiplying by the value of 3. Next, we find the absolute error. So 0 minus 0, 0, 3 minus 2, or 2 minus 3 will be, absolute value will be 1, and here it will be 2. If we take the square error, we find the error 0, 2 minus 3 squared 1, 4 minus 6 squared 4. So according to this error, we can find that we are far away from the real or desired output for our training at this stage of training, of course. Now, as a result of having this error, we don't know exactly where to go, either to increase or decrease W. Suppose that we go and increase the value of W and make this W, let's say, as see here, W equals 4. Okay. We repeat the same stages. Here we have, when we have 4, So these are the outputs of the model when having the weight equals 4. And here we have the square error values when having this weight value specifically, and the square error when we have, let's say, W equals 3. As you see here, we have the error has been increased. So when we compare the errors here, compare the square error in these cases. Let's take another. Okay. Now, if we compare the outputs here, in case of having 3 W for a value of 3 and the value of 4, here we see that the error has been increased. So this means that we need to reduce this value in order to get lower error. So we go down, we already have 3, let's have a value of 2. Again, we can calculate the error. Okay, here we get the absolute error for case 3, here the square error for case 3, and we now find for the when we have W equals 2, so we multiply by by a value of 2. So we get here the square error will be 0, because 0 minus 0, okay, and 3 minus 2, and 4 minus 4. This will give us, of course, here we have, I think it's this value must be 2, because we have here we multiply by 2. So this value will be 2 in the table. Okay, so our final error will be 0. Of course, this is not the case, not very pretty like this output or this error in real applications. However, this is just as we entitled this presentation slide as propagation, back propagation for dummies. This is why we selected simple example, very simple example. So as we have seen in this slide, selecting a value, roughly speaking, W equals 3, we got an error. Now we see that the error after selecting the second value, which is W equals 4, we increased, we saw that there's an increase in error. We tried to reduce the value of W, and we took the value of W equals 2. It looks like that W equals 2 is the minimum that gives us the minimum. Of course, we have selected integer values. This is not the case when we deal with neural network systems, because there we have we pick floating points, and the process is repeated many times, and the number of iterations will be depending on the task that we are doing and performing, and this may take maybe few iterations, maybe tens or hundreds. It depends on the application itself. So we now figure out whether we need to increase or decrease the weight. As we have seen that it has reached a minimum, and we can stop at this point, and there's no need to modify or to update the parameter W. Now, if you may sometimes reach a value or a point, not for a simple, we have here only one W value, where the weight is going, if you further update, the error will be increasing. So you need to stop at this point and need to not to continue and assume that these at this stage the final values are obtained and has the W values and let's say the B values and the activation function parameters also have been fine-tuned. So if you look at this curve, you can see that when you modify the value of the weights, let's say we have one weight, and if you decrease the weight, in this case, the error, for example, is going to be reduced until you reach a value where it's minimum. When you pass this minimum and go in increasing the weight, this will lead to increase the error or square error in this case, which is the loss function, the cost function in our situation. And this means that at this stage you can decrease the weight to reach the minimum, or you can increase the weight to reach the local minimum, the global minimum, and you can decrease the weight if you are walking at the other side. So if you randomly pick a value of W at these locations, you need to increase until you reach this minimum value. If you randomly have selected values at these places, this means that you need to decrease until you reach the global loss minimum. In this case, we have the square error function as a cost function. So how to select a cost function to minimize the error? This is a very important topic when dealing with backpropagation. What will be the cost function, or what will be the loss function also that can be used in order to assume or to get the neural network being finalized at the training stage. Now let's take a deeper view. Here we have a network of 3 layers: the input layer, 0 layer. So we have one hidden layer. This is the output layer, and here we have some checkpoints for the system. Now, in this notation, I want to zoom the slide a little bit. Here, this is our network. So here we have at the left-hand side, we have the x values, x1 and x2. Here we have the weights W1, W1, 2 and W2, 2 and W2, 1. The intermediate stages for the layers in this case. Here we have the value z, which means the obtained sums, the weighted sum, and the a value or the a operation is the activation function. We have a1, a2, and the basis b1 and b2. If you look at the notation here, I see that, for example, for W2 1 subscript or superscript 2, now the W21 means that you link the previous node at layer 2, for example, it will be at layer and the previous layer with the next node in this layer. So we are, if we are at layer 2, no, W21 means that you use a weight that links the previous node, which means that node 1 with the next node, node 2. The same thing for Z. Z means that Z2 is the weighted sum at node 2 at layer 2. So these notations can be used. We'll try to understand and comprehend the main ideas of the backpropagation from these slides. Now, if you look at this box at the upper left corner, we have x values. Here we have a matrix or a vector or maybe a tensor, x1, x2. In this case, we have this is x1 and this is x2. We have y outputs. Here we have the output y1 will be at this place and y2 at this place. Because these are for as a checkpoint, it's not a layer. Y dash or y hat is equal to y1 dash and y2 dash or hat. This is the predicted outputs. This is the targeted outputs that we will try to maybe the opposite, the pre-learned, yes. These are the learned outputs at every stage or run, while here the predicted outputs that we are supposing to obtain, if possible, of course. And these z values, where we have here, for example, z1, 1, z2, 1. This means that this is the z1 value at layer 1, with the node 1. The subscript is 1. Here for Z2, we have Z2 at layer 1, Z2, which is at node 2 at layer 1. The same thing for W. So you see that W11 it is linking the node at this layer. W12 is this branch. So at layer 1, we have W21. It bridges the node 2 with node 1 from the previous stage, and so forth. Here, where A values, the A values are A11. Here we have A11, A21. which means the activation functions for the branch A1 at layer 1 and for the node 2 or branch 2 at layer 1. And the same thing for A12 and A22. Now, what is y? Here y is equal to y minus e. So this is the cost function between the predicted output with the pre-learned output. And we denote this as, suppose that we have, it's a virtual layer here, as E13 and E23. This is E13, so this will be related to Y1, and this will be related to Y2. We suppose that it's at layer 3. In this case, we are not going to use 3 layers. We have only 2 layers, as we will see now in this in the next show. So this is layer 0, this is layer 1, and this is layer 2. And the backpropagation is done using the cost function, the L, or the, it looks like L, the thick L, and we try to minimize our errors using this cost function. In simple words, this is the blue direction, means we have feed forward. So if we are going to find, for example, y1, it will be y1 will be equal to a1 at stage or at layer 2 multiplied by z1 at layer 2. It's clear from the description here. This is y1 output. Okay. Similarly, we can find the output for y2. This is the output, the pre-learned output at this stage or in this network. And then we want to find the error. It looks like E subscript 1 of the superscript 3, which means it looks like a third layer, but it's not true. In fact, it's just annotation. So we want to find the error between the estimated or the calculated or the obtained y1 with the predicted one. And the same thing is on the other side. The other branch. It is the error between y2 actual and the predicted or the targeted output y2, which is y2 hash or dash or what you call it. Okay, this is the feed forward. Now to find the back propagation, we need to trace the map of the error with respect to W11. So we are going to modify W11, W12, W21, W22, and we want to find, as a result, the modification or the error rate for Z1, Z2. Similarly, we want to find for A1 and A2. If you look at the animation here, the error will be traced back to map the change, in this case, just for W1. You follow the animation. This is the error for in respect to W11. It will be equal to the error in respect to A1 at second layer, to A1 in respect to Z1 at second layer, and this will give us the error for W1, or in terms of the W1. Now, how we can read this? If you look at this equation here, this is a partial derivative because we have many parameters here. So when we want to find the first derivative or the rate of change, we take the error in respect to the error rate of change in respect to W1. And this can be done because we have 3 different parameters that are changing, which is A, Z, and W. So let's have a look on mathematical background. So suppose that we have we are asked to find, let's say, the error, we use del operator del y over, for example, we want to find the rate of change of del y over del, let's say, z. We have, in this case, we can write del y over del z, and we may have intermediate parameters in between. Let's say del x and here del x for the same thing. So in order to find the first derivative of y in respect to z, when having more than one varying parameter in this system or in this problem, we need to find the rate of change or the first derivative del y over del x multiplied by del y del x over del z. Now we have del e in terms of del w11. So we have del e in respect to del a, because we have the activation function parameters values will be changing, multiplied by del a over del z, because the output z, the input z to the activation function will be modified according, z will be defined as the sum values coming from w multiplied by the inputs with adding bias. Then del z when defined in respect to W1, let's say for del E or del 11 or del, you can call it any value, no problem. So this is the case where we can find the rate of change in the error between the outputs for simplicity for first branch is equal to the multiplication dot product of the errors in respect to A, the activation function, the error in the activation function in respect to its input, which is Z. Now, and the error of the summed input in respect to its input or the acting parameters, in this case will be W. This is for W11. What about other values? We have W11, W12, W21, and W22. This will give us a sort of a matrix or a vectorization form in order to find the total error in respect to all these parameters. This is just for two branches or for two nodes. What will happen if we have hundreds, maybe more or less nodes? In this case, the operation must in the backpropagation will be a little bit complex and requires a lot of calculations. However, it leads to better performance and improves the system or the neural network output performance. Now, tracing the map for error in the main weights. So now we'll combine all these weights as you see here. Just a minute, if we go back, we have seen this, I think, yeah. So del E over del A, del A over del Z, del Z over del W11. This error is in respect to the weight W11. Now we need to trace for all other weights. So this is for del E over del W12. This will be for W in respect to W22. Now for W21, as you see here, we have ordered the errors in a matrix form. In a matrix form, having these equations defining the error in this situation. Now we can reorder this and try to apply vectorization. Vectorization is a sort of, in order to, because we have a lot of parameters in this case, and we can, it is repeated in some manner, we can write this in a matrix form, and with this we can apply this in MATLAB, in Python, with a very quick actions, because the dot product, even the cross product in these equations, in these softwares, we can see that it works very effectively, better than using loops or other type of programming skills. So this is our equation. As see here, we have ordered the errors in a matrix form. This will be the dot product of these errors in respect to A, errors of A in respect to Z, and errors of Z in respect to the W11, W12, W21, W22, and this will give us finally the output matrix form of the error. We now figure out whether we need to increase or decrease the weights and apply the operation again and again. Now, this operation, it's clear for us. I think now it's is common that this will represent the error in respect the del operation in respect to the activation function and the z value, because it comes from the weights, and here this will be related to the change in z or rate of change in z in respect to the input w values. This is a very simple matrix form, can be done at the second stage. It looks like this one. And for deeper details, you can see the link here in this box, and it will be repeating the same process. However, what we are interested to know that the backpropagation calculates the error in respect to all these changing variables and try to figure out how to reduce the value, or how to reduce the error and improve the performance by making the outputs, the real outputs or the actual outputs, very close to the targeted or the predicted outputs. This can be done using the backpropagation steps. We can here repeat to have a more generalized formula. As you see here, that we combine all the errors in terms of delta L and delta 1L, delta 2L. And this equation will be vectorized this way. As see here, we can write this as a dot product between delta L1 and delta L2. L means the layer, and one first branch or node at the upper neural network part, and delta 2 at the lower. So when we have only two inputs at this stage, so what will happen if we have a lot of inputs? What will be the situation? This means that we need to program this, and I think it's now very well programmed in MATLAB, in Python, in all these programs. You can find the backpropagation. You just need to apply the parameters that are required, and you can just run very easily. Now we talked about the error. So what are the types of errors that we can use, or what are the type of cost functions that we can find or need to find in this case? Of course, here just a few words when we talk about the loss function. For example, let's go to this one. When we talk about the loss function between, let's say, y and y dash, this will involve all values of errors between, let's say we have we take the absolute error yi minus y dash I for all I. Okay. So our cost function in this case is the absolute error function, and the loss function is used here is the cost function that will be implemented in this situation. What are the types of loss functions that can be used? You can see here we have a lot of different cost functions that can be used. We can use the mean squared error loss, mean squared error logarithmic error loss, mean absolute error loss. Usually this can be done when we deal with regression task. In case of applying binary classification, in binary classification, we may use the cross entropy, the binary cross entropy, the Hang loss, squared Hang loss. Of course, here these things will be clarified in next lectures. In case of multi-class, we are going to use multi-class cross entropy, multi-class sparse cross entropy, and we may use the Kullback-Leibler divergence loss. We have other types of losses of loss functions or cost functions that can be used. We'll talk about this later on in future lectures. Now to recap all what we have said before, as see here, we have the input, we have the inputs x1, x2 up to xn. Here are the inputs here, as see xn, x1, 2 up to xn. Okay, applied to the neural network, multiplied by weights, maybe added to some biases. Maybe this is the bias, in this case, or maybe x0 as a bias value. Then we apply to the summation of the network. This will give us the z value. Next, in terms of this shape or this equation, then we apply to the activation function that we have denoted it as A. We find the output O, output which was Y in the previous slide, and we get the output. Now, once we have the output here, Y, and this is Y dash, Y hat, it will be fed back as an error del L, the same notation, will be going to update all weights in all cases here. And after updating these weights, we'll go back again and check the system. If the error is decreasing, we can decrease or modify the value accordingly, and until we reach a minimum. In case of when this value will be, or this minimum will be increasing, we can stop at this point. And there's a problem actually in this case. Sometimes we may be trapped in a local minimum, so we might not always get the global minimum easily. Especially when we have a specific or complex, let's say, inputs with complex features that cannot be easily classified or applied to regression tasks. So in this case, we need to be careful when we deal with such cases, and there are a lot of solutions to bypass such situations or reduce its effect. What we call it the fitting issues. Here I see that we have this is a regression problem. You see the red ball here is the if we talk about this ball is the value of the error. So this is, for example, W, and we want to find its effect on our line regression solution in this case. So by modifying the location or the value of the weight, by default we are varying the or modifying the error value. This will lead to modify and change the regression fitting curve. Let's go back again. For classification tasks, the same thing is true. Now, if you look at this value is, this is the error, and this is, let's say, W. As you see that we have here applied clustering or maybe classification issues, we classified properly the two sets of it looks like either clustering or a binary classification task. Finally, by modifying this these weights, the error, which is the red ball, is changing also. As see here, it's going to a minimum, and as you see that the classification is improved by reducing the error in the back propagation track, and this helps us to modify and improve our performance of the system. Here we have the value in 2 dimensions. As you see that we are targeting this error minimum, And we are at this location at the top, or at point A, and we try to move toward point B by varying or by updating the value of the parameters in this function. And as you see that by increasing, by modifying the value, by applying backpropagation, we are lowering the loss function or the loss value and improving the system performance and reduce the error at this specific task. Here you can find many links, selected links that help in defining more details about the cost functions. You can see here a lot of types of cost functions in machine learning. You can see activation functions in terms of loss function, in terms of the activation. All these things can be found in these links, as you see, and hope it will be very enjoyable for you. And I try to simplify as much as I can to describe and to comprehend the main concept behind the back propagation. I think that's all talks for today. And if you have any questions, please send to me mails or maybe on the MS Teams of our group. So I hope that I'll see you next on the next lecture, inshallah.